Hello, we are solving here today shear and moment diagram problem. So we are given this beam and it has a hinge support at point B and a pin at point C and a fixed support at point A. So we are asked to solve, we have to draw the shear and moment diagram. So we are going to solve this problem in two parts. In this first section, we are going to solve only the reactions, and then the next video we are going to draw the shear and the moment diagram. So let's get started. So to get going, you know from basic statics that point B is a hinge support, it's a hinge connection. That point does not provide moment. As a result, you can divide this beam into two from point B. So you solve point A to B separately and point B to C separately, just to give you a background. And so when you do that, you realize that you are going to have two unknown in this section. Point A to B will give you two unknown because there's a moment here, MA, and there's a force, there's a force reaction there, AY. And that give you that as two. But on this section BC, which is the right section, you are going to have only one unknown. So you can start with that section and solve that, and then transfer your known value for the internal shear at point B. Transfer it to the first section of the beam, and now you can, with that, you will be able to solve the other two reactions here. So let's start. Without drawing additional free body diagram, let me just introduce my shear at this point here. All right. So I'm going to have shear here. I'm going to assume it's positive, and then obviously it's, let me assume this one is negative. I'm going to assume this one here is negative. I'm going to assume this one here is positive. Okay. All right. So that's my internal shear VB at the hinge support at point B. So what do I need to do now? So if I take the sum of moment or sum of forces, you can do sum of moment or sum of forces, you are going to arrive at the value of C. So let's do sum of moment, because since we know that the sum of moment at B is 0. So sum of the moment at B will be the uniformly distributed load multiplied by the length. That will be 3 times 8, that will be 24. And then you multiply by the arm, the moment arm, from the center of this beam to the point of your reference, which is point B. So that will be 4. So that is 3 times 8, that's 24, multiplied by 4, that will give you 96. And it's going to be making a clockwise rotation about this point. And based on my own predetermined orientation, that will be negative for me. So it's going to be negative 96. All right? So let's take care of this. So now I have CY, my CY, that's for CY. This force will make a counterclockwise rotation about this point with a moment arm of 8 feet. So that will be plus CY 8 feet. That will be equal 0. There's no any additional force along here. We have this. Your moment point is here, so that it doesn't contribute to that moment in one case. And in particular, there's no moment at a hinge support. So this is what you have. So with this, you realize that C, your force at C, your reaction at C will be this value, 96 divided by 8, which is going to be 12. Keeps. And it's positive. So that means our assumption is correct. So this force is positive. So now you know this one here. You know this force CY is 12 kips. The next thing you need to know, you need to sum the forces, the sum of the forces in this section. With that, you'll be able to come to determine what the value of VB is. So sum of the forces along the y direction will be VB, okay, VB, this force, this uniformly distributed load, 3 multiplied by 8, that's 12. 3 multiplied by 8, that's 24, minus, and it's negative because it's acting downward. So it's 24. And then we already know what our CY is plus 12 equals to 0. Okay? So when you do the maths, you realize that VB is equals to 24. That goes to the other side of the equal sign. It becomes a positive. This becomes a negative. So you have 12 kips. It's also positive. All right? And it makes sense. If this force is acting downward, 24 kips, then you need 24 kips to act upward in order to have that equilibrium. And so this 12 plus this 12 acting upward counterbalance this 24 force coming down, the uniformly distributed load. So we're done with this section here. So now this force, this VB, we know what it is now. So we transfer to the other side. When you transfer it to the other side, it become an opposite. The magnitude of the force stays the same, stay as 12 kips, but the direction is now opposite. So now the VB on this side will be negative 12 kips. So negative 12 kips. So what can you do to solve for the force at AY? All right. So you could do sum of the forces in Y. We are dealing with this now, with this section AB. Some of the forces there will be AY. You assume that AY is going up, is positive, minus this point load, 8 kips. All right. Now I said this force, this VB transfer here become a negative force, so it's acting downward. So negative 12, that equals to 0. Okay, when you do the math here, you realize that AY is equals 20 kips, because when you move this to the other side of the equal sign, it becomes positive, and it's positive. So we know AY, force AY is 20 kips. All right, so we know that force. We know this force. This is an internal hinge. You don't really need it for your diagram at this point, but we know what it is. So now, what is the moment? The moment MA. So this moment here, let's assume this moment is a clockwise or a counterclockwise moment. So counterclockwise moment, MA. Moment MA at this point. So let's sum the moment in this section to be able to arrive at what the value of MA is. So sum of the moment at point, let's say point B. Sum of the moment at point B. Since we know the moment at that point is 0. So that gives us 8 multiplied by 5. That's and it's turning counterclockwise about this point. So that's a positive. That's 40. Now we know the value of the force AY is 20. So 20 making a clockwise rotation about this point. That will give you 20 multiplied by 8. That will give you 160. Okay, and then we have a concentrated moment, a couple 5 kip foot, and it's making a clockwise rotation about this point. So it's a negative. And then we have MA, which I said assume is positive, plus MA is equals to 0. Okay, when you do this maths, you realize that MA will be 125 cube foot. All right. Okay. That's 125 cube foot. Because we have this value, we have you subtract that value, you get 125. So we know what our moment is, we know what our reaction is. So the next thing is to solve or to draw out the moment diagram. So please stay tuned in the next video. Thank you.